The robotics and autonomous system thread, to me, is a very specific kind of engineering problem. How do you build a system that operates in a physical world on its own? In conditions that are too demanding, too precise, or too dangerous for humans to handle directly? This question has interested me for a long time, long before I had the vocabulary to actually describe it. When I was young, I kept on building things that tried to answer the same question. A smart cane that would guide visually impaired around obstacles. An irrigation system that operates according to the soil conditions without someone being in the field. Each of these projects had the same core idea: sense something, make a decision, and act on it. What this thread gave me was a rigorous framework to my intuitions, that what I was doing instinctively had a name, feedback control, and a mathematical foundation and some engineering principles that once you understand them, you see them everywhere. The way I understand robotics and autonomous system now is through three layers that every autonomous system has to get right simultaneously. The first is sensing, gathering accurate and timely information about the environment. It sounds straight until you realize that the sensors do lie. They drift, they saturate, and they pick up noise. Getting clean and reliable information in real time is its own engineering discipline. The second is planning, making a decision based on that data. This is where control theory comes in. The insight that changed how I think about this is the feedback loop. A well designed system doesn't act on what it knows, it constantly compares what it intended to do versus what it actually does and corrects the difference. The self correcting behavior is what separates the system that is robust from the one that fails the moment something deviates from the ideal conditions. Third is acting, translating a decision into physical motion or output. And this is where the abstraction meets reality. The world has friction, voltage drops, and mechanical tolerances. The gap between what your code says and what the hardware does is where most of the autonomous systems fail. Understanding how these layers interact and how do you design one system that is stable under uncertainties is what this thread is really about. This thread is urgent because it tackles a problem where human lives are online. In disaster response, which is exactly where my project Ares comes in. The goal is to send a machine into an unstable building or a chemical spill first so that the human responder doesn't walk in blind. The core technology for it already exists. The real engineering challenge is making it reliable enough to trust when failure is simply not an option. Ares was my way of taking that theory and wrestling with the physical hardware. Building it taught me things that you don't learn in textbooks. I dealt with gyroscope drift that ruined the heading calculations, motor asymmetry that causes the robot to veer off course, and communication protocols that stall the main control loop. Solving those using calibration, proportional feedback controllers, and asynchronous web servers was a direct, physical encounter with sensing, planning, and acting. It showed me exactly how theory breaks down into reality and how engineers fix it. Ultimately, the most valuable thing I'm taking from this thread isn't just how to tune a PID loop or filter sensor noise. It is absolute confidence to look at highly complex, unpredictable physical problem and know exactly how to engineer a solution.